Assalamu alaikum. It's our seventh lecture of principal methods and applications of nuclear tracks. In this lecture, we will overview about the beta decay, we will discuss about the gamma emission, and then we will discuss about the internal conversion. Then we will move on towards the orbital electron capture, and finally we will discuss about positron decay and carbon dating. So these are our subtopics for today's lecture number 7. So first of all, let's start with the beta decay. Okay, so basically in beta decay, what basically happens, nucleus simultaneously emits an electron. Okay, because nucleus outermost shell there is an electron, but when a nucleus simultaneously emits an electron or a negative beta particle like beta minus 1, and it and with an anti-neutrino. Okay, so both of these particles are created at the moment of nuclear decay. So when nuclear decay, so it emits an electron, you can say like beta particle, or with emitting of an anti-neutron. You already know that beta decay is denoted by this. Okay, this is the original beta decay, and when an electron emits, it beta decay plus with an emission of anti-neutrino. But if beta plus, so it decays with the neutrino. Okay, not anti, because we have to conserve charge. Okay, so this is basically the beta decay. We have an example for you. So our example is basically of beta decay is basically cobalt 60. Okay, you can see here cobalt 60, mass number, and 27 is the atomic number. It decays into nickel, okay, with an atomic number 28 and mass number 60. So you can see masses number not changes, only an increase in the atomic number after decay. Okay, parent into daughter. So to conserve atomic number, so as I told you, in beta decay electron emits from the nucleus. So electron emits like beta minus. So with the emission of beta minus, there must be an anti-neutrino. Okay, so this is your equation for the beta decay. An example: whenever there is beta minus, it emits with the anti-neutrino. Whenever there is beta plus, it emits with the neutrino. Okay, keep remember this aspects. So how you can find the Q value for the beta decay is basically parent minus daughter. Okay, so parent mass of parent is basically for cobalt minus some of these means minus this and minus this. You can say that parent minus daughter, and let's suppose parent is minus 61.651, and let's suppose the mass for the daughter is basically, just suppose, minus 64.471. So parent minus daughter, you will get your final Q value for the beta decay, and that is equals to 2.820 in mega electron volts. Okay, this is how you can find the Q value in the beta decay. You can also write it as here as basically your Q value is basically the sum of energy for the beta minus plus energy for the anti-neutrino. Okay, because the conservation of energy must obey here. Okay, so this is how you can find the Q value. Okay, whereas E beta minus is basically, E beta minus here is basically the initial kinetic energy of electron, and this is the kinetic energy for the anti-neutrino. Okay, it basically depends on the relative direction of the momenta of the three decay products. Okay, beta minus either anti-neutrino or recoil nuclei. Okay, so this is all about for the beta decay. Now we will discuss about the gamma rays emission. Okay, we have seen one or more gamma photons can be emitted from excited states of the daughter nuclei. Okay, we already know that. Okay, transition for these results we can discuss in this. As an example, in the last two sections we already discussed in a previous section, so in this we will discuss basically about the gamma emissions. So what is basically the actual gamma emission is, when an electron excites, you already know it goes into the excited state, and in excited state it is not stable and it is not stay here for long, so it must de-excite. Okay, so when electron or when your atom is de-excite, it transmits gamma emission. Okay, so when an atom excites, when it de-excites, it emissions of photons, and that photons are so called as gamma photons. So you can say that gamma emission is occurring. Gamma emission is very highly energetic, you all know, because it is highly energetic, so it means it is most penetrating. Okay, most deep inside the material medium. Okay, so this is how, and you can also, by techniques of the gamma spectroscope, you can see different applications of this. Okay, so there is an example for this is, so you can see here an example is that basically TC99, it's in star M. Star basically means your this atom is in the excited state, and what this M is basically means, this is in their metastable state. Okay, so this is in the excited state, it's not stay there for long. So when it de-excite into TC99, so it emits a photon, and that photon is basically so called as the gamma emission. Okay, because an atom in the excited state and in the metastable state not stay for long, it must have to de-excite, and due to the de-excitation emits a photon, and that photon is basically the gamma emission. And there is an example, you have to tell me what's this decay is. Basically CS is 13755 is going into BA 13756. You can see only there is an increase in the atomic number, so whenever there is an increase in atomic number, so must have a beta minus decay. Okay, so and beta minus decay always with the anti-neutrino to conserve charge. Okay, so this reaction is basically beta minus decay, but if atomic number decreases, then you can say beta plus decay with emission of neutrino. You can also find the Q value for this relation is basically Q value you can also find by the del P, means parent minus daughter. Okay, same as we did in beta, and we did the same in the alpha decay in our previous lecture. Okay, so this is how you can find and you can define the relation for beta decay and gamma emission. Now our important topic is basically the internal conversion. What basically the internal conversion is, it's basically the process in which energy of an excited nuclear state, when it transforms, you can say that, to an atomic electron, whose level basically you can say lies about between K and L shell. Okay, so it most likely from K and L shell electrons, it ejects the atom from it. Okay, ejects electron from the atom, and when it happens, then it alternative to the emission of the gamma photon. Due to the electron, you already know, when an electron excite or eject, it emits some photon, and that photon is so called as emission of gamma photon. Okay, from the nucleus. So that photon, what did, they basically remove their own electrons with the gamma emission. This process is basically so known as the internal conversion. In simple words, you can say, when in nucleus, your atom is in the excited state, and when your atom de-excites, it releases some energy, and that energy you already know is so called as the photon, and that photon is the gamma emission. And due to the gamma emission, they remove their own electrons. That atom, means that nucleus, after emitting gamma rays, and that gamma rays are responsible to eject more electrons from their self. this basically concept known as the internal conversion. Okay, and there is a constant alpha internal conversion coefficient. Okay, and that alpha is basically equals to Ne divided by N gamma, whereas Ne is the number of electrons and N gamma is basically the number of gamma radiations. You can also say it as competing. Okay, competing means you can eject furtherly faster. Okay, these, so alpha, your internal coefficient, conversion coefficient, is basically equals to Ne, number of electrons, divided by the number of gamma radiations. Then there is a relation, you can say the kinetic energy, you can denote it by ee, the kinetic energy ee, basically of the ejected atomic electron, the electron that ejected, you can, their kinetic energy is denoted by, let's suppose, ee. Okay, is very nearly equals to the excitation energy, because when the kinetic energy of electron basically equals to the excitation energy, then it ejects electron definitely, otherwise not. Okay, so when the ejected electrons kinetic energy basically nearly equals to the excitation energy, you can say by E star. Okay, then this phenomena happens of the nucleus. Okay, then of the nucleus minus the binding energy, you can take this binding energy minus how, this is the E star, which is basically the excitation energy, minus binding energy. Excitation energy means how your electron excite from the inner shell to outer shell. Okay, and basically there you have to must minus by the binding energy, because there is some binding energy in between atom with their molecule with their atoms. Okay, a nucleus with their atoms, so you must have to overcome that force, that binding force, otherwise you will not supposed to eject. Okay, those electrons from the shell. So you must have to minus your binding energy from your excitation energy to get your electrons to eject, to give your ejected electron some kinetic energy. So E basically equals to E star minus E binding energy. Okay, so this is all about the internal conversion. Okay, now let's move towards our next topic, and that topic is basically is the orbital electron capture. In simple words, you can say some nuclei undergo a radioactive transformation, you already know, by capturing an atomic electron. So there is another method. So let's suppose let's suppose this is your nucleus, heavy nucleus, and outside shell you can see electron is revolving. When your electron, okay, uh, uh, combines with the, you can say that engulf. Okay, when your electron engulf with the atom of the nucleus, the phenomenon is so known as orbital electron capture. Okay, so you can say some nuclei undergo radioactive transformation by capturing an atomic electron. Okay, from their K shell. Okay, by emitting a neutron. You already know this concept. Okay, we already discussed these details. So this phenomenon is basically called as orbital electron capture. So in this you can see example PD46103. This is, okay, an atom of the nucleus. It engulfs with an electron from the outermost shell, and after engulfing it becomes RH45, and it goes into the metastable state 103m. Okay, with the neutrino. Okay, you can see here is beta decay, here is beta. So beta is always with the antineutrino if this is on one side, but if beta's other side, so there must be neutrino. Okay, so that's why neutrino. Then this metastable state, not for long time, because when atom is in the excited state, it must have to de-excite. So you can see after that radium is de-exciting into RH10345 again, with an emission of photon, and that photon is basically the gamma emission we already discussed upside. Okay, so this is basically the orbital electron capture, in which your electron is basically engulfed by your atom of the nucleus, of the heavy nucleus, you can say that. Okay, so you know that whenever proton atom of nucleus proton engulfed with an electron, it becomes equals to neutron. Okay, okay, so that this basically the case. So this is all for the orbital electron capture. Our next topic we will discuss is basically the what we have to discuss. Another thing is how you can find the basically the q value of this relation of orbital electron capture. You just have to take again. Okay, what is your parent? Parent is basically this, and mass of parent nuclei in our case is pd, so pd plus mass of this electron parent minus daughter. And what is basically daughter is basically our this, so this mass of this. Okay, minus binding energy, because you must have to overcome the binding energy, otherwise you will not eject electron, or you will not engulf your proton with electron. So you must have to overcome the binding energy. To do so, you must have to minus the binding energy, as we did here. Okay, must have to minus binding energy with the excitation energy to get the electron, okay, removed. So here is the same scenario. Okay, so in parent there is mass of this minus daughter masses of this. Okay, masses of these are must given in your problems, and after that, putting these values, you will find the q value of orbital electron capture. Okay, fine. Let's start our next topic, and our next topic is basically the positron decay. And basically positron decay is also known as beta plus. Okay, because it's an antiparticle of electron. What is basically the proton is basically the antiparticle of electron. You know that our nature depends upon particle and their antiparticle must. So if there any particle, there must be their antiparticle exist in this world. So whereas the electron is concerned, their antiparticle is positron. Okay, electron is basically denoted by the beta minus, whereas their antiparticle positron is denoted by the beta plus decay. So here is an example. Some nuclei, such as there is an example of sodium Na2211, disintegrate by emitting a positive charge electron. Your sodium decays and emits a positive charge electron, and that positive charge electron is so called as the positron. You can see your sodium decays into neon 1022. Okay, so there is a decrease in the atomic number, now not increase. Here there is increasing in the atomic number, so this is beta minus decay. Okay, but when there is a decrease in their atomic number, so it must be beta plus decay, means their positron decay, you can also say that. And wherever beta plus is decay, there must be in combination of neutrino must. Okay, you also know that how there is a concept for the antiparticle. The antiparticle concepts comes from the pair production. You know that whenever, if your photon having energy greater than 1.0 mega electron volts, what happens then? It will de-excite your atom into either electron and positron. Okay, because there are two things, a particle and their antiparticle also release. So that's why when we have to find the q value for the positron, how we can find the q value of positron is basically we can find parent minus daughter, but in this case we have to subtract this minus 2 m naught c square. Why minus 2 m naught c square? 2 is basically because two particles are generating in pair production, like a particle and the other is antiparticle. So that's why 2 and m naught c square, which you already know, 0.511 mega electron volts. So to find the q value in the case of beta plus decay, you have to do parent minus daughter minus 2, okay, m naught c square. So this is basically how you can find the q value for the beta plus decay. Now our last topic of today's lecture is basically carbon dating. It's very important. Carbon has three isotopes: carbon 12, carbon 13 and carbon 14. Whereas the carbon 14 is concerned, it's highly radioactive and it's basically unstable. Carbon dating, or you can say radiocarbon dating, is a method of determining the age of objects. Many times you can you can hear that how doctors can figure out the age of some person that early years ago, or how we can find the age of dead plants or anything else. This is all happen with the help of carbon dating, okay. So this is a method of determining the age of object containing organic material, okay, by using a property, and that is basically C-14, carbon 14, okay. So check by we check carbon 14, a radioactive isotope of carbon, and we can check their age, okay. So this basically happens in before. This quantity of carbon 14 is basically restored continuously as the organism live. As we live, so we will continuously restore carbon 14 in our daily life. But this only stop when human is when living organism died, okay. And when we died, then is the chances we stop restoring this, okay. Otherwise we are continuously inhaling this, or we are taking carbon 14, okay. And this carbon 14 is very deadly for our, okay, life, and because the half life of this is 5730 years. It's a very huge time, okay. So that's why it's very deadly for human lives, carbon 14, because it's highly radioactive, it's unstable, it's not going stop. Their half life, you can see, is 5730, okay. Let's take an example. You can see carbon 14 is basically decay is into the nitrogen 714. You can see there is an increase in again atomic number, so it's basically beta minus decay with antineutrino, okay. So this is an example of the carbon 14, how it decays into nitrogen and with an emission of beta minus and antineutrino, okay. So this nitrogen again, you know that nitrogen is the most abundant in our atmosphere. So this nitrogen 14 is mostly in the atmosphere, and this nitrogen 14 in the atmosphere then interacts with the neutrons, which is surrounding our air, and it again became into the, you can see, carbon 14. So our in you can take a review of that is basically, you can see in our atmosphere is mostly all around is basically nitrogen mostly. This is because nitrogen 714 is abundant in our atmosphere, and there are plenty of neutrons in our atmosphere too. So whenever your neutron interacts with your nitrogen 14, you can see what is the product. Your basically the uh, product is basically the carbon 14, which I told you is basically highly radioactive, very dangerous for human life, with an emission of a proton. So this is basically, you can see how dangerous this is for us. Now how you can find basically the half life, okay. There is a relation n equals to n naught minus e power minus kt, okay, whereas k is basically equals to ln of 2 divided by k1 by 2. And what is basically t1 by 2? T1 by 2 is basically the half lifetime. One half life is basically you have to divide it by 2, second half life you have to divide it by 4, third half life you have to divide it by 8, similarly so on, divided by 16, divided by 32, divided by 64, okay, so on. So this is how you can find the half life, okay. Second half life is basically divided by 4, third half life divided by 8, fourth half life divided by 16, fifth half life divided by 32, sixth half life divided by 64. So that's okay. So if your half life for this is for carbon 14 is 5730, so your first half life is basically divided by 2, so it becomes 2865. Okay, so now if you have to find the means your half life time, so what you have to do, you know that k basically equals to ln of 2 divided by half life. Basically half life is this, okay. Second half life you can find it by this scenario, okay. So half life is this, so you have to put half life and k is ln of 2 divided by half life, and you will get the value of k, and this is equals to 1.21 multiplied 10 raised to power minus 4 per year, okay. Now what you have to do is just have to put this value in exponential e power minus okay, kt, because you want to find t. So how you can find t? First of all you have to take natural log, okay. After taking natural log, cancel with this exponential, and this become ln of n by 2, and this ln divides here and this also. So to find the relation of t, the time, so this is the final relation of time, okay. T basically equals to ln of n naught divided by n divided by nt log natural log of 2 multiplied by t power 1 by 2, means the half lifetime you have to put. N naught is given, n is also given, and putting all values you will get your time. So this is how you can find the age of some sample, okay. So this is the formula that scientists, doctors are using to find the age of any sample, okay, in this world. So this is the main formula, okay. So this is how you can find the time age of some sample, okay. And to plot and so this like plot will occur. You can see your carbon 14 will, this is x-axis in time in years, and this y-axis is basically carbon 14 remaining, okay. So this is how it decays with respect to time, okay, exponentially decay. You can see here t1 by 2, okay, here again 1 by 2, so on, okay. So this is basically our today's lecture number 7 of working principles advance of nuclear tracks. In this lecture we discuss about the beta decay, okay, their equation. We discuss how we can find the q value, okay, how we can find the q value, and then we discussed about the gamma emission, how gamma rays occurs. We find a formula for the q value, how to find the q value for gamma emission. We see some examples for beta decay, okay. Then we discussed about the internal conversion, okay, of material. We discussed the formula alpha, which you know that the internal conversion coefficient that equals to Ne by N gamma, okay. So then we discussed a new concept, and that concept is basically the orbital electron capture. We discussed in electron capture that electron must be engulfed with a proton of the nucleus, okay. So whenever this happens, so this is known as orbital electron capture. So for that you must have to minus your binding energy with your excitation energy to get your electron, okay, removed. And then we discuss about the antiparticle, how antiparticle occurs, what is the phenomena of the antiparticle. We discuss the antiparticle of electron like positron decay. we discussed how we can find the Q value of the positron decay and so on. And at last we discussed about the carbon dating that is very harmful for human lives, and how doctors and scientists and many other researchers finding the age of the sample. Okay, this is how we can find the age of any sample. So that's all for lecture number 7 of nuclear tracks. So that's all for today. We will discuss more lectures soon. So thanks for watching. Stay tuned with us. Allah Hafiz.